Swayam Prabha. Digital India. Educated India.
So, welcome to the 41st lecture on cryogenic engineering under the NPTEL program. We were talking about instrumentation in cryogenics, and in the earlier lecture we were talking about the sensors for temperature measurement at cryogenic temperature levels. And in the earlier lecture we have seen non-metallic sensors like silicon diode, Cernox, ruthenium oxide. We have seen in detail how do they function, how does silicon diode function, how does Cernox function, what are the advantages and disadvantages of these various sensors are. So, we found that silicon diodes have negligible I square R losses because they got a 10 microamp current flowing through it. Cernox RTDs offer high response time and have low magnetic field induced error. So, whenever there is magnetic field, Cernoxes will be preferred. Some of the sensors used for liquid level also, when we saw the liquid level sensors to monitor the cryogen level, we saw the principles on which dipstick, hydrostatic gauge, electric resistance capacitance gauge, thermodynamic gauge and superconducting liquid helium gauge, how do they function, how do they represent, how do they indicate the cryogen level or the liquid level. Now, going ahead from temperature and cryogen levels, in this lecture we are going to talk about pressure measurement. So, pressure measurement is a very important task in cryogenic engineering. However, we are not talking about positive pressure, but we are talking about vacuum pressure, that is negative pressures, and then we will conclude this particular topic of instrumentation in cryogenics. So, there are various thermophysical properties that are measured or monitored in cryogenics, and they are, we know, temperature, liquid level, pressure, mass flow rate, viscosity and density, electric and thermal conductivity. Out of which we had said that we would see temperature, liquid level and pressure in details, while others, because these are the three which are normally used in all cryogenic experiments. So, the first three are going to be dealt, out of which we have already dealt with temperature and liquid level, and in this particular lecture we are going to talk about pressure. So, this particular lecture is going to be on pressure measurement in cryogenic engineering. We know that cryogenic vessels are insulated closed containers. Whenever I keep cryogen, we know that it has to be well insulated, it has to be absolutely closed, so that the heat radiations or any other radiations will not come over there, there will not be any convection, the heat inleaks will be as minimum as possible, so that the boil off is kept minimum. Besides temperature and liquid level, pressure is also a vital aspect in cryogenic engineering. The pressure measurement is needed to check whether the level of vacuum is maintained, because we have seen that vacuum is used everywhere, and therefore vacuum monitoring is very, very important, and therefore pressure measurement is required to see if the level of vacuum is retained all through. If there is any leakage, vacuum will be broken and no experiments can be conducted in cryogenics, because the moisture will come inside, all kinds of losses will happen, and therefore the experiments will not be able to be carried out. Also, we measure pressure to monitor the pressure rise inside a container as there is a continuous heat inleak. So, if the boil off increases, if the heat inleaks increase, the pressure will rise in the container, and that also can be monitored if we found that this is the important parameter to be monitored. However, there is normally a safety valve which will open if the pressure exceeds a particular predetermined value. So, this can be normally taken care of, while this is the most important thing to be monitored. Pressure measurement in cryogenics deals with both pressure above atmosphere and pressures below atmosphere, which is vacuum, which is what we were talking about. Cryogenic insulation topic, we have seen that cryogenics and vacuum go hand in hand. So, wherever cryogenic experiments are done, we have seen that most of the cases will have vacuum around it. Every cryogenic equipment therefore needs a vacuum gauge for pressure measurement. So, wherever a vacuum comes, we will talk about the order of vacuum. What kind of vacuum are you talking about? -2, -5, -10, and therefore it needs to be monitored, and therefore vacuum gauge is very, very important. So, every cryogenic, most of the cryogenic experiments will need to have a vacuum gauge with it. Basically, it will come with a vacuum equipment also, a rotary pump or a diffusion pump or a cryo pump, they will have the vacuum gauges. So, vacuum gauge, vacuum pump, vacuum device is an integral part of a cryogenic experiment, and therefore, it is very important to understand how does a vacuum gauge function, what kind of vacuum gauge should I purchase for my system, all right, how costly it is it required in this particular application, what kind of vacuum gauge, what principle of working should be there. All these things have to be monitored to select a particular vacuum gauge. Various vacuum gauges and their working principle therefore are discussed in this topic, because vacuum gauge becomes very important device to be used in the cryogenic instrumentation, and therefore in this particular chapter, in this particular lecture, we will discuss various vacuum gauges and their working principles, so that you understand which vacuum gauge we should select for our particular application. As seen in the earlier lecture, the levels of the vacuum ranges from atmosphere to 10 to the power minus 12 millibar or less. For different levels of vacuum, we have different gauges working on different principles. This is the most important thing. If you got a level up to minus 2 or minus 3 or minus 4, I can have a particular gauge. If I am talking between minus 4 and minus 6, I got a other principle or vacuum gauge working in that on a different principle. And if I want to measure vacuum of very low grade, that means minus 9, minus 10, minus 11, etc., then I have to have a different kind of a vacuum gauge. And therefore, it's very important to know on what principle these vacuum gauges work. For example, up to a particular level of vacuum, thermal conductivity gauges can be used. So, up to minus 3, I will say thermal conductivity gauge can be used. Therefore, the choice of a gauge for a particular application or for a particular vacuum level is an important aspect. If I want to go up to minus 9, I should use an ionization gauge, and therefore, principle of the working of that particular vacuum gauge is different than as compared to the principle on which thermal conductivity gauge works, and this is very important. Okay. So, different pressure vacuum gauges which could be used are hydrostatic gauge, which is a McLeod gauge, which is a most primary gauge to measure vacuum. Diaphragm gauge, we can have a mechanical gauge or an electrical gauge also. We got a thermal conductivity gauge, as I just mentioned earlier, and then we got a thermocouple gauge. These two are normally would be used up to minus 3 or minus 4 levels of vacuum. Then we got a ionization gauge, and under ionization gauge we got a thermionic ionization gauge, and we got a cold cathode gauge. Now, all these gauges are actually representative of various other gauges. Actually, there are various other gauges are also used, but most of them would work on a principle similar to this. So, in minus 3, minus 4, I will have something similar to this. In very, very low vacuum or very low vacuum gauges, you will have a principle would almost kind of similar to these principles, all right. And therefore, there are some minor advantages and disadvantages related to vacuum, the process, life and the accuracy. Now, let us see one by one on what principles these gauges work. Hydrostatic gauge is one of the oldest type of vacuum gauges. It is also called as McLeod gauge. The schematic of this gauge is as shown in the figure, and it works on the principle of simple Boyle's law. Boyle's law, PV is equal to constant, P1 V1 is equal to P2 V2, temperature remaining constant, all right. So, this is what everybody knows. Now, this is a schematic on which the McLeod gauge works, and we can see the schematic as well as we try to understand the schematic as well as try to understand the principle on which this particular gauge works. The gauge consists of a glass U tube, which is what you see here, all right, whose left arm has a spherical bulb of a known volume. So, let us say this is a U type and this is got a spherical bulb of a known volume. The right arm is branched into a capillary tube. So, the right arm, and then is one more branch which is a capillary tube over here, and this again joins back the main arm. The right arm is branched into a capillary tube to monitor the minute changes in pressure. The capillary is marked with a zero tolerance, zero reference point. Okay, you got a zero reference point over here. It culminates back into the right arm as shown here. So, this capillary again culminates into the right arm as shown. Alright, now this reference point, zero reference point also actually is in line with the top of this arm. So, this is always what we call as zero reference point. Now, the lower end of U tube is connected to a mercury reservoir equipped with a piston. So, this lower end will have mercury, and this is connected to some kind of reservoir where the piston moves up and down. So, that this piston motion up and down will control the motion of the mercury in and out of this device or this gauge. This is actually our gauge, while this piston will basically see that mercury is going up or down. So, that with the motion of this piston you can monitor the filling and emptying of this U tube. Initially, the apparatus is filled with mercury up to the indicated level. So, we can see that you got a mercury up to this point before the branching happens. So, now I see that the mercury has come up to this, and I will adjust this by pushing this piston up and down. So, the mercury has been filled up to this point, and the pressure working volume of which the pressure has to be measured, of which the vacuum has to be measured, is connected to this place. So, my experimental device or whatever the cryogenic volume on which experiments are being carried out, in which I want to have vacuum, this volume is connected to this place. All right. So, let us say we want to measure this P1 value. Let the vacuum pressure to be measured is P1. It is applied on the right arm as shown in the figure. All right. Now, this pressure sees entire volume over here, and therefore, the entire volume here is at pressure P1, which is a vacuum pressure actually. In this situation, the pressure at any point in the system is P1. Now, with the application of piston load, when the piston is moved down, mercury now will move up. With the application of the piston load, the mercury level in the apparatus rises, and we are bringing up from here to here first, just to understand that now the gas in this region is now detached from right arm. All right. So, there is a gas depending on whatever vacuum level we have. This is the volume of the gas which is fixed. All right. We know this volume very well. I know the volume of this, I know the volume this, I know the volume here, and I know that now some volume has got trapped, which cannot be now seen from this side. All right. So, when the mercury crosses the junction, when the mercury has crossed this junction, a known volume of gas is trapped inside the bulb and the tube. So, this much volume, which is the volume of this tube plus the entire bulb, I know a known volume has been trapped now in this case. Let this volume of the gas be V1 as shown in the figure. So, now here we have got a pressure of P1 and we have got a volume of V1, because P1 was initially maintained. We just came up and we know that there is a volume of V1 over here, and we know that P1 V1 is the volume, pressure and volume respectively, that is going to be here. Therefore, initial condition now is going to be pressure at P1, volume at V1. All right. I am sure you are clear about this. With the further application of piston load now, the mercury rises to fill up both the arms. So, now I will press this down and the mercury will come here, the mercury will come here. The load is applied until the mercury level in the capillary tube reaches the zero reference point. So, I will go on pressing this piston till the point that this mercury goes up and occupies position up to this. All right. Depending on the vacuum level over here, depending on the whatever load I give, I will ensure that the piston is pressed to such an extent that the mercury will come here and stop at this particular point. My zero reference point, as soon as mercury comes up to zero reference point, I will stop pushing this piston down. So, the load is applied until the mercury level in the capillary tube reaches the zero reference point. Let us see what happens now. All right. So, now I have reached up to this point and I am stopping the motion of this, the pushing of this piston. Now, what has happened? Whatever volume was there, P1 and V1, now this gas which was previously over here is getting compressed to some pressure over here and some volume over here. I will know this pressure, I will know this volume, and now I will do further calculations. The mercury levels in the arms are adjusted to suit to the applied vacuum in the right arm, compressed gas in the left arm. So, I will do this motion in such a way that I have some significant volume over here in this arm, and also I ensure that applied vacuum is taken care of. So, I can do this piston movement in such a way that these things get adjusted. In this condition, the volume of the gas in the left arm is read directly from the available scale. So, now I got some scale over here which tells me that the volume of the gas in this left arm has a height of h, and I know the area over here. So, I can calculate the volume of the gas that is being trapped over here. So, there will be a scale over here which can be directly read, the value of h can directly be read from that, and one can compute the volume therefore. That is, the difference in the mercury levels in capillary and left arm represents volume and pressure of the gas in the left arm. Right? The difference in the mercury levels in the capillary and left arm represents volume and pressure of the gas in the left arm. So, I can calculate the pressure at this point, right, which is going to be pressure at this point and which is equal to P1 plus corresponding to the height of this. This is my new pressure now, all right, because this is exposed to pressure P1. The pressure at this point will be P1 plus the pressure corresponding to height h, and the volume I know because I know the cross section area of this, I know the height of this. So, I know both pressure and volume associated with this volume in this left arm, alright, and I know now in P1 V1 is equal to P2 V2, and I can do further calculations. Let A be the cross section area of the tube. We have final condition as pressure at this point is going to be P1 plus H equivalent, and volume is going to be A into H. Alright, these are my final conditions of pressure and volume respectively. Hence, applying the Boyle's law to the left arm, we have initial condition pressure P1 volume V1, final condition pressure P1 plus H volume AH, PI VI is equal to PF VF, initial PV is equal to final PV. So, P1 V1 is equal to P1 plus H into AH, P1 V1 is equal to P1 AH plus AH square, simple algebraic thing. Rearranging the above terms, we have P1 is equal to AH square divided by V1 minus AH, and this AH term is very small as compared to volume V1 because V1 is a very big volume, alright. The term AH being very small as compared to V1 is neglected, and therefore, we have, I will neglect this, and therefore, P1 is equal to AH square upon V1, and therefore, we can say now the pressure P1 which we wanted to measure is a function of H square, and I can do a calibration accordingly, and I can compute the value of P1 therefore. So, directly as soon as this is connected, I can adjust these things, have the value of H, and now H is going to be representative of the pressure we are talking about, because A is known to me, V1 is known to me, they are constant basically, alright. So, pressure can be read directly as a function of now H square, and this is the way the pressure in a basic principle, using this basic principle can be read by using a simple Boyle's law, but then we have to see that the gas obeys Boyle's law. The advantages are the gauge reading is independent of the gas. Whatever gas I use, I don't have to bother about it. I can get the pressure reading done. It serves as a reference standard to calibrate other low pressure gauges. I can use this technique to calibrate other sensors also, and there is no need for any zero error corrections. There is nothing called as zero error connections. Everything we are doing by pushing the piston up and down, I do all the measurements. The disadvantages are the gas should obey the Boyle's law, as I said, which is important. That means the gas should be an ideal gas, and it does not give a continuous output. So, whenever I want to measure, I will do the piston up and down, and therefore, I will not get a continuous reading. If the vacuum breaks, I will not get a knowledge about this, because every time I will have to measure the vacuum whenever I want to. There are some disadvantages of this particular McLeod gauge. Okay, coming from McLeod gauge now, let us see other gauges also. For example, we have got a diaphragm gauge. The schematic of a diaphragm gauge is as shown in the figure. So, we got a diaphragm which is shown over here, we got a working space here, and we got a vacuum to be measured, alright, and we got a P reference point over here and some signal at this point. So, it consists of a low stiffness corrugated Teflon diaphragm, which is my diaphragm over here. On the left side of the diaphragm, a reference pressure P reference is maintained. So, I got some reference pressure on this side, and I got some vacuum or some pressure which is to be measured on the right side of this diaphragm. On the right side, the diaphragm is exposed to the test pressure, alright. So, the test pressure is the one which we want to measure. In this device, a deflection is caused by a pressure difference across the corrugated diaphragm. That means, you will have some pressure difference between the pressure to be measured and a reference pressure on this side. Depending on this pressure difference, this corrugated diaphragm will go up or down. It will come on this side, it will come on that side, depending on who is higher. Now, this deflection of the diaphragm actually is getting calibrated. It will send a signal to our measuring device, and that is the simple principle of a diaphragm gauge. This pressure signal or the deflection is amplified either by mechanical or electrical arrangement to read the pressure directly. So, simple diaphragm motion is going to be amplified, and it will fade to some kind of a signal which could be mechanical signal or electrical signal, and this is a simple principle of diaphragm gauge. The amount of diaphragm's deflection decides the accuracy and sensitivity of the gauge. So, how much deflection occurs will show the sensitivity of the device. So, if you got a mechanical arrangement to see the motion of this diaphragm, you can have some gear arrangement, you can have some needle and things like that, and that can be used. In a mechanical diaphragm gauge, the diaphragm's deflection is magnified to a mechanical pointer and a scale assembly. The scale is directly calibrated in terms of pressure for a direct reading. The operating range of this gauge is going to be from 1000 to 1 millibar with a good accuracy. all right. Instead of mechanical, I can have some electrical signal coming out of it. So, in this case, I got a different arrangement over here on the left side of the diaphragm, all right. So, here the schematic of a capacitance diaphragm gauge is as shown. So, whenever I got an electrical signal I want, I can use a capacitance diaphragm gauge. So, depending on the motion of the diaphragm, the capacitance on the left side will change, which will be representative or which will be calibrated to tell me what the pressure is there on the right side. So, it consists of two capacitance electrodes in the form of concentric circular disc D, which is what you see. All right, there are discs D and A also, circular annulus A. So, you got two discs, one it D and annulus A. All right. These two electrodes are deposited on a ceramic substrate S, and you can see there is a S ceramic on which these two capacitance electrodes are placed. All right. These two electrodes are placed in the close vicinity of an inconel diaphragm. So, you got a diaphragm which is this and it is connected to this. Now, the circular annulus capacitor is grounded at G and this is going to be grounded at G. The whole assembly is connected to an AC electrical bridge in which a change in capacitance is calibrated directly in terms of pressure. So, whenever there is a motion of diaphragm, the capacitance change would happen over here. And this capacitance change is going to be connected to a AC electrical bridge, and whatever changes happen in the capacitance depending on the pressure change on right side, it will be shown up over there, or this capacitance change directly can be calibrated in terms of vacuum pressure, and that is a simple principle of electric diaphragm gauge. Therefore, in an electrical diaphragm gauge, the deflection is fed to a movable capacitance assembly. These gauges are more reliable and accurate as compared to the earlier design. Need not be any mechanical assembly, there will not be any gearing mechanism or anything like that. It is just the capacitance change which may be amplified and fed to a signal, and directly the reading of the vacuum on this side can be taken using this electrical diaphragm gauge. It is important to note that the accuracy and sensitivity of the gauge is independent of the composition of the gas. All right. So, basically this assembly does not see the gas. The gas pressure just presses this inconel, or inconel motion is occurring only with the gas. That is it. The composition of the gas does not come into picture. Now, let us come to the other aspect, which is thermal conductivity gauge, and this is quite commonly used gauge, thermal conductivity gauge. Now, it is based on a simple principle that this figure shows. What is this figure show? It shows, the figure shows the variation of thermal conductivity of a gas with residual gas pressure of N2. So, we have got a gas pressure given over here, and this gas pressure and thermal conductivity of the gas, the variation of the thermal conductivity of the gas with this gas pressure acts as a principle on which this particular thermal conductivity gauge works. The x-axis denotes pressure in torr and y-axis denotes logarithm of thermal conductivity. All right. So, these are logarithmic scale of thermal conductivity of the gas, while the x-axis gives the pressure. So, you can see the pressure in torr -1, -3, -5, etc. Now, what you can see from here, when you got a pressure range of 10 to the power -3, the variation of the conductivity is almost linear, approximately linear, while above that it is flattened and below that also it hardly shows any change. But when it goes from 10 to the power -3, this variation is quite linear, approximately. From the figure, it is clear that for the pressure between 10 to the power -2 torr, the thermal conductivity decreases, that is A, and this decrease is approximately linear for the pressure range. For this pressure range, this decrease is approximately linear. So, what is linear? The variation in conductivity. The conductivity varies linearly for this particular pressure range, and therefore, this conductivity change can be considered to calibrate the pressure. So, whenever the conductivity change, the Q conduction will change, and therefore, that Q conduction will be indicative of the pressure during this pressure range. That is, K gas is directly proportional to the pressure in this range. Once you say K gas, the heat conducted by that gas is a function of K gas, and therefore, Q conduction through the gas is directly proportional to the gas pressure in this range. So, if I can calculate Q conduction, if I got some representative value of Q conduction, I can relate Q conduction to the pressure of the gas. Pirani gauge works on this above principle, and therefore, Pirani gauge always works on thermal conductivity, and very commonly Pirani gauge is used up to 10 to the power -3 torr pressure measurement. Alright. So, thermal conductivity gauge also is called as Pirani gauge. In this gauge, a tungsten filament is placed inside the residual gas of which the vacuum level is to be measured. Now, how does it function? So, we got a tungsten filament which is placed in the gas, and this is residual gas in around this pressure range 10 to 10 to the power minus 3 torr. So, you can see this is a filament in this, and I got a gas around this of which I want to measure the pressure, and this tungsten filament is fed some current, and therefore, it will get heated now. It is heated to a high temperature by passing an electric current. So, I will pass some electric current through this, and I got a gas around this, because of which heat transfer will happen. Now, depending on whatever I am doing heating, the gas will try to cool it, and the amount of Q that is going to be conducted is going to be a function of K of gas or thermal conductivity of gas. And we know that in a given pressure range, the thermal conductivity is a function of that pressure range. So, if I could get the temperature over here, or if I can have some representation of this Q conduction, this temperature also will change the resistance of this filament. Alright. So, change in the resistance of this filament is representative of Q conduction, which is representative of the temperature at this point. So, it is heated to a high temperature by passing an electric current. The temperature of filament, thereby its resistance changes with Q conduction. So, whatever Q conduction happens over here will change the temperature and thereby the resistance of this particular filament. Now, if I put this particular element in a Wheatstone circuit, alright, some imbalance will get created because of the change of resistance of this, and this will be indication of the pressure at this point. The Q conduction is a function of K gas, which directly represents the pressure. So, ultimately the change in resistance of this filament would represent the change in pressure. Alright. This filament is connected to one of the arms of the Wheatstone bridge as shown in the figure. So, now I can put this filament and this resistance in the Wheatstone bridge, and I have got some voltage, and I can see the imbalance D because of the change of resistance over here, which will happen because of the change of pressure in the residual gas around here. With the change in the resistance, the equilibrium of the bridge is disturbed at D, which is directly calibrated in terms of pressure. The bridge can either be a constant voltage type and a constant current type. So, you can have a constant voltage or constant current over here, and this is the principle on which thermal conductivity gauge works. Very commonly used Pirani gauge works on this principle. Similarly, now instead of monitoring the resistance over there, I can monitor directly temperature, and that is called as thermocouple gauge. This is also very commonly used. Basic principle is same, but instead of having Wheatstone bridge, instead of monitoring resistance, I can directly measure the temperature by putting a thermocouple there, and this temperature would indicate me the pressure, because Q conduction will change temperature. Just measure the temperature and get the value of pressure. The thermocouple gauge functions on the same principle as that of Pirani gauge, that is the effect of residual gas in cooling a heated filament. This is what exactly we are talking about. The change in the temperature of the filament due to the change in the surrounding gas pressure is measured directly by a very fine thermocouple. So, what we were doing in Pirani gauge, change in the pressure would change in the temperature, change in the temperature would change the resistance of the filament, and this resistance change will be captured by the Wheatstone bridge. Now, here I am not going up to resistance, I will just monitor the temperature by putting a fine thermocouple over there, and this temperature change or a thermocouple temperature will tell me what is the pressure over there. The thermocouple is attached to the center of the filament, which represents an average value of the temperature. This thermocouple voltage is magnified and it is calibrated to denote the pressure reading. So, whatever temperature I see because of thermocouple, it can be magnified and you can see the pressure reading directly. The operating range of this gauge, of this Pirani gauge as well as thermocouple gauge, is between 5 to 10 to the power minus 3 millibar. The application of thermal conductivity gauge are widely found in the rotary and soft pumps. Most of the pumps will have Pirani gauge or thermal conductivity gauge. This is widely used up to 10 to the power minus 3 millibar. In these pumps, these gauges are used for continuous monitoring of backing line pressure. They are commonly used, continuously used. The advantages of these gauges are a fast response time offered by these gauges. They offer an appropriate solution in case of control applications. Because there is a fast response, you can take corrective action immediately looking at these gauges, and therefore, they are always used in some control applications. These gauges are often preferred due to their robustness. They are low cost devices also as compared to other gauges. So, after Pirani gauge, thermocouple gauge. Let us see thermionic ionization gauge, and let us see the principle on which it works. In an thermionic ionization gauge, the residual gas molecules are ionized using an electron beam. Simple principle, ionization. So, you got a simple principle of A. In the above reaction, we see that A is a gas molecule. So, A is a gas molecule which is hit by an electron, as a result of which A gets ionized to A plus, and you got 2 electrons. So, you can see that as soon as the electrons are bombarded on this gas molecule, you got ionized current. You got a plus and 2E minus. Alright. So, we can see that some ionization current will getting generated as soon as the gas molecule A is bombarded with some electrons, and this is a simple principle of thermionic ionization gauge. Here A is the gas molecule of the residual gas, E minus is the ionization electronic beam, and A plus is the ionized gas molecule A plus, while 2E minus are the electrons in the electric circuit. This reaction produces 2 different types of current. They are I plus and I minus. Both will be called as ionic current. And this is a simple principle. What we are doing basically is bombarding electrons on the residual gas molecules and producing this current. When we measure this current indicates the amount of molecules were there. That means the level of vacuum. This current will actually be indicating the level of molecules or the pressures over there. And this is the principle of thermionic ionization gauge. So, ionization gauges, for the measurement of vacuum pressure, there are 2 types of ionization gauges. They are thermionic ionization gauge and cold cathode gauge, both based on the principle how are these electrons produced. Alright. So, here we heat them and produce electrons. Here we got a high potential across cathode and anode, and electrons gets produced. These gauges operate accurately up to very low pressures, typically in the order of -3 to -10 millibar. So, these are gauges which are used for very low pressures, for very low vacuum up to -10 millibars. While the earlier one which we have seen, they were up to -3 millibars. So, the principle of its working, it is thermionic ionization gauge. The schematic of a thermionic ionization gauge is as shown in the figure. It consists of, as you can see here, a filament, grid and collector, 3 elements. It consists of thermionic filament F, cylindrical open mesh grid G. So, you can see a grid over here which has mesh kind of thing. So, it has got some porosity associated with it, and then what we have is ion collector C, alright, and the working gas, the residual gas will be around over here. So, what is happening? The thermionic filament F emits the electrons to ionize the residual gas. When heated, the thermionic filament F will produce the electrons, and these electrons will travel from here to here, and they will ionize the gas around here. The mesh grid G traps the electron to measure the electron currents. This grid actually ultimately will trap all the electrons coming on it, and this will measure the electronic current. The filament is charged with a positive potential of plus 30 volt. The grid is maintained at a high voltage which is 180 volt over here. This large positive potential difference is required to accelerate the electrons in least possible time. Alright. So, they got high voltage over here, and therefore, the electrons will come over here in as fast as possible. The ion collector C is earthed in order to maintain a 0 potential, while this is at 0 potential. Alright. So, high potential in between, you got some potential at filament F, and this is earth at 0 potential. Now, the electrons are emitted from F after heating and are accelerated towards the grid. So, these electrons which will get accelerated towards the grid, and you can see this grid is a mesh kind of form. The majority of electrons strike the grid. However, a few of the electrons move beyond the grid now. Some electron will come out of it, and how do they come out? Because of the porosity. Due to the porosity of the grid and high velocity of the electrons come out very fast, and because of the porosity, they will come out of this grid also, and they go beyond it. These electrons enter a region of decelerating field. Once it comes out, you got a high potential here and a 0 potential on the collector side, and therefore, they will get decelerated. Their motions will come very, very slow now. The velocity will decrease further. These electrons enter a region of decelerating field in between the mesh grid G and the collector C. They oscillate back and forth. Now, here these electrons will go back and forth because of the decelerating field. It will not have any particular direction as such, and therefore, they will spend most of their time in this region between the collector and the grid. During this phase, the electrons have a maximum probability to hit the residual gas molecules, which produces ionic current. So, if you remember the first slide, when we talked about thermionic ionic gauge, A will be over here, gas molecules A will be over here, the electrons will come and strike, and we are basically increasing the probability of hitting these electrons, hitting these molecules by these electrons which are now decelerating field, and therefore they will spend more time over here, and therefore there will be high probability that these electrons will strike these molecules and ionize them. This ionization current represents the ions in residual gas. So, when electrons strike the molecules, ions will get formed, and therefore ionization current will get formed, and these ions will ultimately come on the grid over here, alright, and therefore that will measure this ions E also will come on this grid G, and this will be indicative of the ionic current, which will talk about the pressure of the gas in this particular area. This ionization current represents the ions in the residual gas. This is directly calibrated to read the gas pressure. Alright, so ionization current is going to be indicative of the gas pressure over here. These gauges are used from 10 to the power minus 3 to 20 to the power minus 7 millibar, thermionic ionization gauges. The advantages of these gauges are, it offers a high reliability and ease of operation. Very simple. It can be easily degassed by electron bombardment. So, the gas is going to come on this and get stored on this, and this gas can be taken care of. It can just remove this gas so that this is ready to the face next bombardment by just have power 35 watt, hit it, and the gas will be released basically. All the gas which is captured over here can get released out of it will get clean, it can get easily degassed. These gauges offer a linear calibration current and pressure. So, ionization current is going to be linear variation with the pressure, and again therefore the calibration becomes very simple. And this is the principle on which thermionic ionization gauge works. The disadvantages of this gauge are the use of hot filament. This filament is going to be hot, because when it is hot, then only it will release electrons. The use of hot filament increases the risk of burning out. Sometimes it can get burnt out, especially when it is exposed to atmospheric air and you got oxygen over there, and you can have some burning of this filament also. So, normally this will be used in the molecular region from minus 3 to minus 8, minus 3 to minus 7 millibar, but by mistake if it gets exposed to atmospheric condition, that means you start right from the beginning this gauge cannot be used from room temperature or from ambient pressure, but if it happens, somebody just press this button, the filament can get burnt, because it will be surrounded by all oxygen high density gas. The use of hot filament increases the risk of burning out when exposed to atmospheric air. So, once the filament is gone, you cannot work, you cannot use this particular gauge, you have to replace this filament. So, many times this gauge will come with an extra filament also, but this is a very costly element, and therefore working with these gauges should be very carefully handled. Alright. As a result, an extra filament is provided as a standby, but then it costs. Alright. So, thermionic ionization gauge always has these problems. One has to be really expert to handle these gauges. The chemical reaction within the residual gas at high temperatures produces undesirable gases. Because of the generation of high temperature, sometimes there could be some reaction also between the residual gases, and that also should be avoided. So, there are some risks associated with this usage of this thermionic ionization gauge. Now, let us come to the next one, which is cold cathode ionization gauge. As the name suggests, it is cold. Well, the earlier one what we talked about is hot, and therefore we had some problem. So, all these problems can be taken care of if we go with cold cathode ionization gauge, and this is normally used as a very powerful gauge called penning gauge. Alright, so penning gauge works on this principle. As mentioned in the earlier slide, the thermionic gauges exhibit a risk of burning out of hot filament. This led to the development of cold cathode ionization gauges. These are also called as penning gauges, which are widely used at very low pressure. So, every device which wants to have a pressure of minus 6 to minus 7 will have a Pirani gauge and penning gauge as combination, Pirani penning. So, Pirani will measure the pressure up to minus 3, while from minus 3 to minus 7, Pirani will not be used now and penning gauge will be used. And this is generally observed two gauges that will come on every machine, every vacuum equipment. Okay, let us see how it works. The schematic of a penning gauge is as shown in the figure. So, the schematic, you can see that it has got a cathode, and therefore it has to have some anode also. It consists of an anode ring as shown over here. So, this is the anode ring, a circular anode ring. It is placed between the two symmetrical cathode plates. So, you got a cathode plate, top and bottom, and in between anode. The cathode plates are grounded at G. You can see grounding at 1G. So, you got a positive, negative and grounding at G here. The anode is charged with a potential difference of 2 kilovolt. The high potential between cathode and anode has 2 kilovolt potential difference here. Now, in this so we got an electrical field which is coming over here. In addition to that, what we have is a magnetic field. An actual magnetic field of about 0.05 Tesla is maintained across the entire setup. Alright, so we got a magnet on this side, magnet on this side, we got a magnetic field at perpendicular direction to this. So you got an electric field, you got a magnetic field, and therefore the motion of electrons is going to be subjected to electrical field and magnetic field also. Very often a permanent magnets are used to provide this field. The combined crossed electric and magnetic field produces an increased length of travel of electrons. So when operation starts, the cathode will release electrons and they will go to anode. But because of this magnetic field, they will take a large time, a very long time, they will take a long time to reach from cathode to anode from other side. Alright, and this increases the probability of hitting the electron as we saw in earlier case. This increases the probability of ionization. So you got a working gas of which you want to measure the pressure would be here. And what we want to do basically here is to see that the electrons going from cathode to anode because of high potential between them will hit these molecules, and we want to increase the probability of hitting these molecules because of application of magnetic field. Because the electrons are moving in a magnetic field, they will go in a very spiral way. They will go up and down spiral way. They will take a very long time to reach from cathode to anode. This will increase the probability of electrons hitting the working gas molecules. This increases the probability of ionization. The electrons are finally collected at anode. Alright, so cathode electrons get released, they will go to anode. Because of magnetic field around there, they will take a long time to reach anode, and during this travel from cathode to anode, they will hit the molecules, and thereby the electrons will finally be reaching up to this, and they will ensure that each electron hits the molecule. This ionization current represents the ions in the residual gas. This is directly calibrated to read the gas pressure. So once the ionization current reaches over here, it is representative of the pressure of the residual gas over here. And this is the principle on which the cold cathode ionization gauge works, or the Pirani or the penning gauge works. This gauge is widely used for many scientific applications in the range of -3 to -7 millibar. The advantages of these gauges are it is very robust, no thermionic filament. The biggest advantage of this is there is no filament, there is no heating of filament, and therefore there is no filament need not be sacrificed, need not be burnt basically. Alright, so you got a simple cathode and anode, no thermal radiation, no heating business involved over here. The disadvantage of this gauge is it is normally less accurate than the thermionic gauge. So if this is tolerable to you, then it's okay. If you want a very accurate vacuum measurement to be done, in that case you will have to go for a thermionic gauge in that principle. So after understanding how the cold cathode ionization gauge works, or how does a penning gauge work, I just want to show you how does it work basically, and whatever we have just learnt you can see in actual case. So this is how a penning gauge looks like, and this I would connect, this portion I would connect in a line of which I want to measure the pressure. So if I want to measure the pressure up to -6 millibar, -7 millibar, this element, or this is the penning gauge, or this is the head of the vacuum gauge, is going to be connected over there, and this will be sensed in what we have an arrangement for cathode and anode here. So here if you can see at the center there is anode, and on the other sides we have got a cathode. I don't know whether you can see, but please try to imagine that you got a cathode over other side, alright, to which the voltage is given from this side. So the voltage is given over here, while the anode is going to come at the center, and the ionic current is going to be measured from here and connected to the gauge. So this is basically kind of a head, and you can have some gauge where this ionic current which is going to come at anode is going to be measured. Also what you see from either side is the magnet. You got a permanent magnet over here. So you can see the magnet, you can see the cathode, the cold cathode, and what you see in the middle is the anode, and you got a high voltage which is supplied to the cathode from this side. So whenever the electrons get released from cathode to anode, the residual gas will come in between and it will get ionized, and this ionization current is going to be fed to the gauge over here, which is calibrated as a function of this residual gas pressure. Now, these electrons, when they leave from cathode and go up to anode, they will take lot of time because of this magnetic field. They will not go straight from cathode to anode, but they will go in a spiral way. They will take a lot of time because of magnetic field over there, and this magnetic field is therefore responsible for that. This electron, while traveling from cathode to anode, will ionize the gas molecule, and depending on this ionization current getting produced because of this heating of electron to the molecule, ionization current will be there, and this ionization current will be fed to the gauge, which is going to be calibrated in order that we know what is the residual gas pressure over here. And this is the way the penning gauge works. This is the way the cold cathode ionization gauge works. The conclusions that could be drawn from the entire topic of instrumentation: in cryogenics, there is a need to monitor various properties like pressure, temperature, liquid level, etc. for safe operation. Thermocouple works on Seebeck effect. This is what we saw. We have seen PT100, PT1000 are some of the commonly used RTDs in cryogenics. So, we have seen thermocouples and RTDs that are normally used up to 30 to 40 Kelvin, from room temperature to 30 to 40 Kelvin temperatures. Some of the commonly used non-metallic sensors are silicon diode, Cernox, ruthenium oxide. So, for lower temperatures now, below 30-40 Kelvin, to have a very good measurement, these are the sensors that could be used, which are silicon diode, Cernox and ruthenium oxide. Sensors used to monitor liquid level are dipstick, hydrostatic gauge, electric resistance capacitance level gauge, thermodynamic level gauge and superconducting liquid helium level gauge. We have seen how these level gauges work. We have seen the principles of their working. And in this particular lecture, we have seen different pressure oblique vacuum gauges used, and we have seen the principles of working of McLeod gauge, diaphragm gauge, thermal conductivity gauge, thermocouple gauge, thermionic ionization gauge and cold cathode gauge, of which, as I told you, the thermal conductivity gauge is called as Pirani gauge normally, and cold cathode gauge is normally referred to as penning gauge, and these are normally used to measure the vacuum up to -7, between -3 to -7 millibar, while thermocouple gauge and thermal conductivity gauge will be used up to -3 vacuum. So, up to -3 we can use thermal conductivity as well as thermocouple gauge, while cold cathode gauge and thermionic ionization gauge could be used up to -7 millibar. Pirani and penning gauges are used for high vacuum levels. For less vacuum levels, other gauges are used. Thank you.